Okay, so we continue with our study of the chemical bond. The next type of bond is molecular bonding. Also known as covalent. Covalent meaning a sharing of the electron clouds. So we find, for example, hydrogen with its one electron wanting to bond with another hydrogen, and of course, what do we call a single bond? It doesn't matter whether it's a ionic bond or whether it's a covalent bond. It's an electron pair. So these two electrons would pair, and we would of course have the basic standard state of hydrogen, and this would be your bonded pair, called a bonded pair. And of course it's the diamagnetic spin relationship. Spinning electrons. The energy changes associated with covalent bonding are illustrated in a classical graphic that I want to show you. This is in all the classic textbooks. And the horizontal line is your distance between nuclei, and we'll call that R, like that. This is energy released or gained in the verticals, which we use a symbol, or the community, the chemical community or physics community uses this symbol called psi, and he puts a plus on it for endothermic. So these are gaining energy if you're working in this end, or losing energy, put a minus down there as a subscript. It's just symbolic. But one is endothermic or gain of energy, and one is loss of energy as the bonding process takes place. Okay, so when we're out here somewhere with two hydrogens that are infinitely apart, the bond interaction, there's no interaction. So we want to put a dot here so there's no gain or loss of energy in the process. But as these two begin to come together, the two nuclei approach, then we see that energy is lost as these two come into closer contact. So this is an exothermic event that's taking place. And so we would put a dot, say, down here as the approach, indicating that energy is lost as the two nuclei approach, and then they begin to overlap. Let me move that a little closer over there. Not just touch, say, in the nature of the two nuclei in here. So they are at some distance away, and so the amount of energy drops in here. And then they'll reach a point at which, well, I guess I can put it down here, where they will overlap to an optimum position between, and that's called your bond length, RB, between the two nuclei. Because it's like taking two balloons and pushing them together. The centers can only go so far without exploding, of course. And so if you visualize pushing two balloons together, maybe you could find a kind of an equilibrium point in there at which the two nuclei would rest comfortably. Well, at that point, we have the maximum amount of energy lost. And that's called the bond energy, delta E bond, or delta E subscript B bond energy. Now, if you shove them, continue to push them closer together, assuming that, the balloons didn't burst, you would push and push, and the balloons would push back on you. It's like a coil spring. If you start squeezing the spring in, it pushes back on your hands. And so you start gaining energy then, and it gains very rapidly over the span till you reach the origin. It never really gets there and goes to infinite energy. So this is what kind of keeps the covalent bond at what we call an equilibrium distance between nuclei. And so this would be your and so you would see a trend as the nuclei approach and would follow this path. Kind of rough graphic. Well, that's what happens when two nuclei approach. The amount of energy, however, varies with the two nuclei that are coming together. In the handout, you should have this handout, bonding energy. And so with this, we can determine how much energy has already been calculated by somebody else for various types of bonds. So what I want to show you is, like in the hydrogen-hydrogen bond, if they come together, it gives off, now this is an interpretive table. In forming a bond, it gives off so much energy forming the bond. But if you want to break that bond, now listen to, you have to put the same amount of energy back in. So if you're forming a bond, the energy would be labeled as exothermic. If you're breaking the bond, it would be labeled as endothermic, but they're equal. So if you're forming the bond, this would be labeled as a minus 432 kilojoules. But if you break the bond, you got to put that same 432 kilojoules back into the hydrogen-hydrogen bond. Well, you can see others in here, carbon and carbon. When they come together, it's 346 kilojoules given off. And hydrogen-nitrogen bond. And so you kind of cross-section all of these, and here's some multiple bonds down here. Carbon can support a double bond, a single bond, and a triple bond. So the single bond, say carbon and carbon single bond is 346, but you go to a double bond is 602. So the higher number of electrons between the nuclei, the stronger the bond. It's called electron density. So when you increase the number of bonds, you're increasing the glue. That's the way I like to think of it. And like a triple bond, it goes up to 835. So when you go to those triple bonds, it's a whole lot of glue between the two nuclei, and so it's a lot stronger bonds. So we can use this to calculate the overall energy transition in the formation of molecular compounds. So we're going to get into Lewis structures here in a minute, but if you have methane, for example, and you drew the Lewis structure for it, It shows a two-dimensional arrangement of elements about the molecule and how they're bonded. A bar represents an electron pair or one covalent bond. Okay? So when you look at this, this represents 4 carbon-hydrogen bonds. And that's 4 times whatever the sheet shows. We go on a sheet and look, and it's 411 kilojoules. So in the formation of one carbon-hydrogen bond, it's an exothermic 411 kilojoules. See, it's interpretive. We hadn't broken. And so that's 4416 exo kilojoules. So when the molecule of methane is formed, it will give up 1644 kilojoules. Now, this is a thermodynamic table, and it's taken from thermodynamic textbooks and on and on. Typically, you need to be aware that there's usually about a 2 to 3% error in these between textbooks. So I'll work a problem later on that you'll see that we get this, and we probably get 1650 or 60 in a different kind of calculation. So I'll show you that when we get there. Okay, and so if you had, say, methanol, this is methane. And so it would be structured in a Lewis arrangement like this. And so if you go around the molecule and you find the bonds, you have 1, 2, 3 carbon-hydrogen bonds. You have 1 carbon-oxygen bond, 1 oxygen-hydrogen bond. 1, 2, 3, 4, 5. 3, 4, 5, right. Then you take your sheet, look up the energies, and this is 1, whatever that carbon oxygen is, 358, and then 1 times, what is that, oxygen, hydrogen, 459 kilojoules, and that's 1233, 358, and 459 kilojoules. And adding those together, we find the total energy given up by the formation of the methanol. So that's a very straightforward calculation, provided you have the table with you. Of course, you will either have that attached or you'll have the energy values attached to the problem. So it's a very simple, straightforward calculation. Just one more, just to show the multiple bond issue. Here's ethylene. And we'll learn the arrangement issue later. So it has 1 carbon-carbon double bond in it. So that kind of makes it a little different. And 1, 2, 3, 4 carbon-hydrogen bonds. We already know those are 411 kilojoules and so forth. And that was 602. I remember that one. So 2 kilojoules. And so you add those together just like we did the previous one. And so just to show you that the same applies to multiple bonds as they do to single bonds. Okay, where am I? Is this handout here, structure in covalent bonding. And it has some notations in here that are kind of consistent with what covalence is and the type of structure. The ultimate objective is to draw out molecules either in two-dimensional or three-dimensional form, so that we can see what the structure is and evaluate that structure as to its chemistry and see how this, and so we see in here covalent molecules define the structure and geometry, okay, about a central element. Hydrogen is never a central element. All bonds are covalent. These are some little bitty rules, but I'm fixing to go through what we call drawing Lewis structures. Once you go through this a few times, it just gets automatic. Lewis structures of molecular compounds. Now, I've been using a method I developed many years ago, and it works very well for writing Lewis structures. And you can find different methods in different locations, and I found mine to be, in my humble opinion, much simpler than anything I've ever seen in the textbooks. And it's called the AVO-BEC, A-V-O-B-E-C method. And as you can see on the handout, is right there in front of you. It means A stands for arrange, valence, octet, bond, enter electrons, and check octet. This is a procedure you'll use right now to draw out Lewis structures. And we'll go back through one you've already seen, the methane, and then progress to more complicated systems. But one thing that's common about this is maybe the first couple of times through may appear to be confusing, but what you will see in doing this is the repetition that's applied to giving you a formula. You write a Lewis dot structure. So that's what the objective here is. How this works is you follow that prescription. Arrange. What you're talking about is arranging the elements in a two-dimensional plat or image around the central element or elements that are presented to you. So it's obvious, and if you notice on the notes above in the handout, hydrogen is never a central element in anything. So if I were to write this, there's only one way to write it, and I could arrange it in here. Now what's important about this is everything must conform to the octet rule, and you'll see how to do that at the end of this. But I could have molecules where I can make many arrangements, but they don't conform to the octet rule. And so that's a trial and error problem that you have to deal with if you're working with molecules and trying to identify structures. For our purposes, I'll probably give you the basic structure and it won't be a problem. But anyway, what you want to calculate is your valence number, which is the number of valence electrons making up the entire molecule. To do that, you notice you have one carbon. I'll start with that one. One carbon and 4 hydrogens. From the periodic chart, carbon has a valence of 4, it's in group 4. So it's 1 times 4. And hydrogen's in group 1, so it has 1. So it's 4 times 1, and all that adds up to 8. Okay? Now you need to get the octet number. That's when everything of all elements is full. And there are only 2 numbers that you will have to consider, 8 or 2. Okay? When everything on the periodic chart, see, we're working primarily with non-metals to the right of the periodic chart. So we're talking about carbon, nitrogen, oxygen, and halogens, and sulfur, and phosphorus, and all of those. When they fill up, they fall under the octet rule, and they achieve the noble gas configuration. So when carbon is full, you take it as an 8. Well, let me put the letters down so you can see that. And so we fill up carbon, and so that's 8 electrons, but hydrogen fills up at what? 2. So we have 4 times 2, and so that will give us 16. And we add all that together, right? Now, what is the bond number? That's the number of covalent bonds in the molecule. And that's octet minus valence over 2. So if you got your octet number, your valence number, take the difference and divide by 2. 16 minus 8 over 2, and so you have 4 covalent bonds in this molecule. And so now you want to enter your electrons or bonds in this step. So I will have a bar here, that's an electron pair, 2, 3, and 4. So that satisfies the number of covalent bonds associated. Now that's the Lewis structure for methane. And then you check your octet or duet. Now to do that, remember, covalent bonding is electron pair sharing or bond sharing. So what I'm going to do is I'm going to circle all the bonds around that are associated with carbon. And how many electrons are in that circle? I got 1, 2, 3, 4 bonds, 2 electrons per bond, that's 8. So it conforms to the octet rule. So we see 8 electrons, and so that's acceptable. And we go to hydrogen and check it. And see how many electrons are in there. Each one has a single bond. Hydrogen fills up at 2 electrons. So that's okay. So that is a valid Lewis structure. Okay? That's how we put it together. Now, what if you have a formula that has multiple Lewis structures? This is not an end unto itself. If you have a formula, I'm going to work one out here and show you. If you have a formula that's given and you can work out more than one Lewis structure that conforms to the octet rule, then you'd have to go to an instrumental method to separate the 2 substances by their properties. But this is only a method in which you can use to draw out the molecule. And there may be several molecules within the structure, in the formula that you can draw for a structure. For example, here, C2H6O. Well, I can draw out 2 possibilities for this when everything's said and done. One is ethanol, and the other is dimethyl ether. They're distinctively different molecules and have distinctively different properties. But you can draw and use the AVO Beck to draw the Lewis structure for each of them, and it will conform to the octet rule. Okay, so the arrangement for, let's do ethanol over here, and I'll put dimethyl ether over there. Well, now like I said, it's a trial and error for the arrangement, but I'm going to give you that because we don't have time to go playing with a lot of different structural arrangements. And dimethyl ether looks like this in its 2-dimensional arrangement, like that. So we've gotten the A out of the way. So what do we need now? Valence, octet, and bond numbers. So the valence for both of them. Matter of fact, here we have 2 carbons, 6 hydrogens, 1 oxygen, and the valence for carbon is still 4. Hydrogen 1, oxygen 6. 20. Everybody good? Okay. Octet numbers when everybody's full. Well, it's either 8 or 2. So only one in here is going to be 2 is hydrogen. Both carbon and oxygen fill up at the octet, 8. So we calculate the octet. I mean, write it out for academics. So that's 2 times 8 plus 6 times 2 plus 1 times 8. 36 is what I get. Okay. Now, the number of covalent bonds is, of course, the bond number, which is simply octet minus valence over 2. You see the repetition there? How we're doing that now? And they all kind of shake out. There's one little add-in that I'm going to put at the end of this to add on to this. But anyway, octet is 36 minus 20 over 2. That's 16 over 2. So this has 8 covalent bonds. And so now we enter in our bonds, which is little bars. Each bar represents a pair of electrons. So let's see. 1, 2, 3, 4, 5, 6, 7, 8. Okay? And over here we can do the same thing. 1, 2, 3, 4, 5, 6, 7, 8. So yeah, we can draw 2 distinctively different Lewis structures for this formula. And which one is it? Well, you don't know. It could be either one of them, so you have to go to an outside analysis, like an instrumental, run it through a spectrophotometer, and it'll tell you, well, this one's ether, or sniff it. You know what ether sounds like, or ethanol. They have their different properties. Now, checking the octet kind of poses a little minor problem. So you can go through here and you can see everybody except right here. What do you do for that? That only has 4 electrons. Well, in this case, you have the privilege, and it's a rule, that you can use non-bonded pairs. The bars here are called bonded pairs, electron pairs. But I can put 2 non-bonded pairs in there, but looks like colons laying on the side, like that. And that's 8 electrons in that red circle. Oxygen, group 6 elements will carry 2 non-bonded pairs. If you look in there, you see oxygen, and if sulfur happens to be in a structure, you can throw a couple of non-bonded pairs in. Nitrogen, and I'll work one here in a minute, it'll carry 1 non-bonded pair. Halogens carry 3 non-bonded pairs, and they fill out the octets. So that's what I'm saying here. Put enough electron pairs in to complete the octet as needed, and pair those as non-bonded pairs. Is what they're called. Okay. So the arrangement on this is ethyl, an ethyl group. And that's going to be hooked to nitrogen, and we're going to have hydrogens as satellites, substrates, as some people call them, around that. So there's our arrangement. The valence number is 2 carbons, 7 hydrogens, and 1 nitrogen. 2 times 4 plus 7 times 1 plus 1 times 7. 22. Octet number, we fill everybody up. Two, 3 makes 24, 34, 38. And that one. Everybody still with me? It's no more complicated than that, guys. I'm not throwing you any curves here. Okay? Okay, so the number of covalent bonds now is octet minus valence over 2. 38 minus 22 over 2. 18. This is 2 from 8 is 6. 1, 16 over 2, 8. 8 covalent bonds. So we go in here and 1, 2, 3, 4, 5, 6, 7, 8. Should have had one more. What did I miss? I must have added this in here. Why I put a 7 in there? But senior moment. Anyway, 20 gives you 9, and so that. The only one that's a problem is, of course, the nitrogen, and it carries one non-bonded pair. So, like that. Formaldehyde. It really is going to look like this. There's your arrangement. Okay, so valence is a carbon plus 2 hydrogens plus an oxygen. That's 4 plus 2 plus. You'll start shortcutting after a while. 6, 10, 11, 12. Octet, carbon plus a couple of hydrogens plus oxygen. That's 8 plus 4 plus 8. 20. Octet minus valence over 2 again. 20 minus 12 over 2. And that's 8 over 2. So we have 4 covalent bonds. But when I start putting them in, we run into a little twist here. 1, 2. I've run out of spaces. Now, knowing that hydrogen is never a central element, nor can hydrogen carry a multiple bond, what you have is one more bond in your calculation, and it goes right here, and it identifies a double bond. So you find a place that will conform to the octet rule. And again, we have the dilemma of not conforming to the octet around that particular one. Everybody else, the carbon, the hydrogens are fine. So this carries 2 non-bonded pairs. Like I say, you can complete that with whatever you need to get to that level. One more on multiple bonds, acetylene. C2H2. Do this one. And the valence is 2 carbons, 2 hydrogens, 2 times 4 plus 2 times 1, 10. Octet, 2 carbons, 2 hydrogens, 2 to 8, that's 2 to 2, 20. So the bond number is octet minus valence over 2 again. 20 minus 10 over 2, or 5 covalent bonds. Well, acetylene is this. That's only arrangement. I'm giving you the arrangement. Yeah, you could write HCHC if you wanted to, obviously. That's not, because hydrogen is never an in-between element. So we won't even consider it. So I need to get 5 bonds in here, and hydrogen can only support single bonds. So where do we put the other 2? Between the carbons. And so there's a triple bond now for that molecule. So you see the consistency in the arrangements here and how these are put together. So what if we came up with NO3 minus? How do you deal with that? Or NH4 plus, the ammonium ions, and those kind of things, or SO4 2 minus, like that. Now that is a pretty broad spectrum type arrangement. But you use the same thing. You use the AVO Beck. except in the valence. You have to add or subtract an electron because of the charge issue. Here, this is negative net charge because it carries an extra electron. Here you have a positive. Well, why is it positive? It's deficient by one electron. Here is deficient by 2 electrons. So when we calculate the valence number, you either add an extra electron or subtract an electron, depending on whether you're working with a cation or an anion. Yes, ma'am. Okay, the procedure now is the same, except that, like I say, at the valence. So let's do NO3 minus, and see how this is the nitrate. So the valence is nitrogen plus 3 oxygens plus an electron, because it's 1 minus. And so that's 5 plus 3 times 6 plus 1. That's 18, 21, 2, 3, 24. Now you're going to have to come out with an even number. If you come out with an odd, recheck your math. Octet, you don't add or subtract anything. It's already full. So that's 8 plus 3 times 8, which is 4 times 8 is 32. So the covalent bonds, octet minus valence over 2, is 32 minus 24 over 2, 8, yeah, over 2, which is 4. Did I get that right? Yeah, 4 covalent bonds. I don't trust my brain. Yeah. Okay, so we have an arrangement. We have 3 oxygens around the nitrogen. And so I got 4 covalent bonds. One of them has to carry a double bond. You can put it anywhere in there as you want to put it. Then fill out with non-bonded pairs. Now, in polyions, or molecules that carry charges, you can use more than what is standard in a neutral molecule. Like a double bond for oxygen will always just carry two non-bonded pairs. But if you have an oxygen with a single, you have to finish it out like that. And it's called a resonance structure, and we'll get to that in the next lecture. But anyway, 1, 2, 3, 4. So that takes care of that. Something's missing. Oh, wait a minute. Something's with it. Anyway, bracket that and put the charge on the outside. Just a symbology thing. Let's go to ammonium. Keep it on the. Here, your valence, you will subtract an electron. So your valence on ammonium is nitrogen plus 4 hydrogens minus 1 electron, and that's 5 plus 4 times 1 minus 1 is 8. And octet is nitrogen. And you don't add or subtract anything on your octet. And so that's 8 plus 4 times 2, 16. So bonds, octet minus valence over 2. Gets kind of mundane after a while. 16 minus 8 over 2 is 8 over 2 of 4 covalent bonds. So you get real routine with this thing. So it's nitrogen, hydrogen, 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 hydrogen. Put your bonds in, bracket, and put your plus outside like that. So that's just a standard notation method is used for polyions and so forth. SO4 2 minus. Now this has got quite a bit of, but you still must conform to the octet rules, what I'm saying. And this has some weird bond structures in it. I'll show you. Valence is equal to sulfur plus 4 oxygens plus 2 electrons this time. 6 plus 4 times 6 plus 2, 32. Octet is sulfur plus 4 oxys, and that's 8 plus 4 times 8, 40. And the number of bonds is 40 minus 32 over 2, and so what is that? 8, 9, 10, 8 over 2, which is equal to 4 covalent bonds. I'll move that up here. So we have a sulfur, and then we'll surround it with 4 oxygens and put our bonds in and fill out our octets around each oxygen like this. Now, you will learn in tomorrow's lecture, when we get to more complex, sulfur can support 1, 2, 3, 4, 5, 6 bonds. And I'll show you in the geometry section how it supports more than just the octet. And so you could have a structure that looks like this. And each one of these is carrying a negative charge. Add those two together and you get your net charge minus 2. It's called a formal charge. We'll do that tomorrow. And I don't know what to do with a formal charge worksheet, but I'll find it.